that it causes the receptor to change shape, to change conformation. And when it does that, that then causes some sort of downstream effect. And so we call this the two-state theory. This says that the receptor can be in an inactive form or an active form, and that the ligand binding causes the receptor to go from inactive to active. Now, an easy way to think about this inactive versus active receptor is to think of an ion channel as our receptor. In this situation, the inactive ion channel is closed and the active ion channel is open. This is a spatial thing where we can clearly see which form is active and inactive. The same idea happens with non-ion channel receptors. We just can't easily look at that receptor and say, well, that one's active and that one is not. So here we're looking at a set of equilibria. And so we have an agonist A plus receptor R. Those come together to form a complex of an agonist with a closed receptor. And the agonist with a closed receptor can dissociate. So that complex can fall back apart into the agonist and receptor separate. Or it can switch to the agonist with an open receptor. And notice these are equilibria, so it's two directions. And so an agonist with an open receptor can go backwards to an agonist with a closed receptor, in which can then go backwards to the two entities being separate from each other, not in a complex. And so down at the bottom, we just see a very simple drawing of an ion channel. And so we see in this situation on the left, the two proteins, or the two parts of the protein come together, essentially touching each other, blocking ions from moving through the channel. That would be a closed or inactive receptor. And on the right, after a ligand has bound, the ligand isn't in this picture, so don't worry about why you can't see it. Now the channel is open. It has changed conformation. There is now room for the ions to flow through the ion channel. So that is the two-state theory. It can be open or it can be closed. It's more complicated than that, though. Receptors can open even when they're not bound by a ligand or an agonist, which means that the receptor can exist in two states on its own, which means that the ligand can bind to either an open receptor, in which case it would most likely keep it open, or bind to a closed receptor and cause it to open. So now we have to add the multiple possible scenarios in. So now rather than being a linear set of equilibria, we have this kind of square-shaped equilibria. Now we can start at any point in this that we want, but in my mind, the most logical place to start, as we work our way through it, is in the bottom left corner, with an agonist and a closed receptor. That is the most natural place to start. So if we have an agonist and a closed receptor, there are two things that can happen. What we saw before was that the agonist binds a closed receptor, forming an agonist with a closed receptor complex. The other is that the receptor, without the agonist binding, spontaneously opens. Now, over in the bottom right corner, we have an open receptor and a non-bound agonist. If we have an open receptor and a non-bound agonist, and the agonist binds to that open receptor, we end up with an agonist bound to an open receptor. Go figure. With our agonist and a closed receptor, that can then cause the receptor to open, and we end up in the top right corner. And so we got to the same place through two different routes. Now, on the equilibria, there are some variables here. Those are telling you which variables determine how much the equilibria favors one side or the other. I do not require you to know which letters go on each equilibria. You do need to realize that these are equilibria. We're going to see a number of different sets of equilibria. This one, we saw one on the last slide. I do expect you to be able to reproduce those equilibria. But what I need you to do is tell me what's at the corners. I don't need you to put the variables on the arrows. And so this was simple two-state theory. This was a slightly more complicated two-state theory. So the idea that a receptor can spontaneously open comes back to the idea that a receptor can have constitutive or spontaneous activity. We can have activity in a system coming from a receptor in the absence of a ligand. And so what this graph is looking at is dose-response curves with one agonist in a number of different systems with the same receptor, but something has changed in each system, changing the amount of spontaneous activity of that receptor. So on the x-axis, we just have increasing agonist concentration. Our textbook likes to use this very, very awkward, complicated unit. Ignore it. As we go to the right on the x-axis, we're increasing the amount of agonists. So that's what you need to realize there. And on the y-axis, we're just looking at the percent open receptor, whether it was spontaneously open or induced open by the binding of an agonist. And each line represents a different value of L. And all L is how likely a receptor is to be spontaneously open. And so a high value of L represents a receptor that likes to open all on its own. There's two important things to notice from this graph. The first is obvious. The higher the value of L, the higher we start on the y-axis. At low drug concentrations or no drug concentration, we have a high amount of receptor that is already open on its own. And so here, without adding any drug, we have maybe 0.6, 0.7, almost 3/4 of the receptor is open on its own. Whereas at a low drug concentration and a low value of L, we have basically no receptor that is open. The other thing to notice is the value of the EC50. So the EC50 in each graph is the little open circle. And hopefully you notice that as we decrease the value of L, the EC50 goes up. And so essentially what's happening here is the more a receptor likes to be open all on its own, the more responsive it's going to be when a drug binds to it. And so we're not going to have to add as much drug to get 50% of the remaining receptors open. What you may also be noticing is that the maximum amount open changes based on the value of L. That is something specific to this particular experiment. That is not a generalizable idea. It is not something I want you to take away from this graph. So that was a two-state model. We're going to make it more complex. We're going to move to a ternary complex model. This does not apply to all situations. Something like an ion channel is going to be a two-state model. It's not going to be a ternary complex model. However, we have things like G-protein coupled receptors, where multiple things have to bind that receptor. The agonist or ligand has to bind, and a G-protein has to bind. So there's three things there in that complex, and so we're calling it a ternary complex model. And so we're going to start with the linear form, and again, this is something I need you to be able to reproduce. And so we have an agonist binding a receptor that comes together to form an agonist-receptor complex, but the G-protein is now off floating by itself. Once it comes in, we now have an agonist-receptor G-protein complex. The G-protein then becomes activated. So here, in this situation, yes, the receptor may be activated when the agonist binds. However, an active receptor, an active G-protein coupled receptor, on its own does not have any sort of downstream effect. It activates the G-protein, which causes the downstream effect. And so we would not see any sort of effect or response other than the ARG complex all the way on the right. Now, when that G-protein becomes activated, it will leave the complex as an active protein, go elsewhere, and do its thing. However, again, it is not that simple. We now have to have an extended ternary complex model. This is, again, something you need to be able to reproduce, but not the letters on the equilibria. Fill in the corners in the middle, the areas between the arrows, showing the different states and connect them. We need to do this because G-protein receptors become spontaneously active. Just like an ion channel can open all on its own, if we have a G-protein receptor that spontaneously activates, a G-protein can bind to that, be activated, and cause downstream effects. And we need to make note of that in our complex here. And so we're going to start, again, in the bottom left corner, but in the real world, we can start anywhere here. So here we have an inactive receptor that's R with an I. And so one of two things can happen. We can have an agonist that binds to our inactive receptor, or the receptor can spontaneously activate. We're going to start with the agonist binding. So now we have an agonist bound to an inactive receptor, which then shifts to an agonist bound to an active receptor. We now have three options of where we can go. We can go backwards. The agonist can stay bound, but the receptor deactivates, becomes inactive again. The complex dissociates while the receptor stays active, or the G-protein can bind, forming an agonist G-protein active receptor complex. Note that we cannot go from an agonist with an active receptor straight back to an agonist when it's not bound to an inactive receptor. We have to go through one of these two steps in order to get back to where we started. If we go back to where we started, the inactive receptor that spontaneously activates, the agonist can bind, and we get back up to the agonist with the active receptor, or a G-protein can bind to the active receptor, in which case we're receiving effect, we're seeing response. Once we're here, the complex can fall back apart, or an agonist can bind. Now you might be thinking, if I can become active without the agonist, what is the purpose of binding an agonist to an active receptor? And that is to help hold it in the active form. Notice, if I am here, there's two directions I can go. I can go here, or I can go here. In both situations, my receptor is active. By binding that agonist there, I'm going to help hold it in this corner as far away as possible from the inactive receptor, keeping my signaling going longer and longer. So I think this is probably fairly straightforward, but you need to be able to reproduce this for me. Yes, your exams are not written, but I can find a way. So this is just an example of constitutive activity with G proteins. I think it's the very next lecture. We're going to talk about this melanophore system. So this is a way that we can measure activity of G proteins. And melanophores are cells that express melanin. And melanin production can be in response to G protein activity. And so what we're seeing on the graph on the right is simply on the x-axis, we're increasing the amount of cDNA that we have transfected into these melanophores. And the cDNA is for a G protein coupled receptor. So all we're doing is increasing the amount of G protein coupled receptor. And the y-axis, again, it's a very, very strange unit, but it is just activity or response. And as we increase the amount of receptor, we increase the amount of activity. There is no ligand here, no agonist whatsoever for our receptor. And so we can measure increased response. And on the left, we see it visually. Increased response here is simply the cells becoming darker. The idea that a receptor can become activated all on its own allows for inverse agonists. An agonist is something that binds to a receptor and has an effect. Originally, we assumed that we were starting at zero effect. And so the only way that an agonist could have an effect is to increase the response, right? But if we're starting at some non-zero number and a molecule binds to it, it can increase response or it can decrease response. If it decreases response, that is an inverse agonist. And it does that by shifting the equilibrium towards the inactive state. So here we have our G protein coupled receptor. Inverse agonists are not specific to G protein coupled receptors though. So here we have our inactive receptor, which can spontaneously form an active receptor, which can then bind a G protein and cause response. If we added an inverse agonist here, it would shift the equilibria to the left. I'm trying to think, on your screen, that's probably to the right, isn't it? We're going to shift this way, to the left on the slide. So if the inverse agonist bound to the active receptor, it would shift it left to the inactive receptor. If it bound to the active receptor bound to the G protein, it would shift it left to the active receptor unbound by the G protein. And because of Le Chatelier and all of his stuff, if we shift this here, we're also going to cause some of what was here to shift over to the inactive receptor. Now, the last model is the cubic ternary complex. And if you're having a heart attack, don't worry. This is not one that I'm going to require you to be able to reproduce on an exam. This takes into account that if we have an active G protein coupled receptor and the G protein is floating over here, this G protein can be sequestered by binding to inactive receptor. So if the G protein is bound to the inactive receptor, that means that it cannot bind to the active receptor. However, this adds another possible route. If the G protein binds to an inactive receptor, the receptor can then spontaneously activate, or it can bind an agonist, causing it to activate. So now we've added kind of a workaround to our extended ternary complex, and if you imagine that, it becomes three-dimensional. I am not going to walk you through it. Surprisingly, if you walk through it, it's not that difficult to follow. I encourage you to do it so that you can really understand what's going on here. But again, I will not require you to reproduce the cubic ternary complex. So if your mind is not blown yet, if your mind is not spinning yet,